Much for being here. So I'm Michelle Bernardino. For those of you that don't know me, I am the STEM and Math Supervisor. I didn't plan words for tonight because I kind of wanted just to speak from the heart. I always get a little emotional this evening because you get to love this group, and this is such a great group of students who've done amazing work this year. As challenging as the past few years have been, they have really risen to the occasion. I'm really excited for them to present to you tonight. After the presentations, you will find them at their tables. Feel free to roam around, ask them questions. They can show you how their capstone projects work. There's some light refreshments at the back table if you want to help yourself to that. Once again, thank you all for being here, for your support through everything we've kind of all been through. Thank you to Mr. Portis, Mr. Hazler, Dr. Sheridan, and our wonderful staff that is here to support the students as well. I am going to turn it over to our superintendent, Mr. Portis.
Good evening. A little taller than Mrs. Bernardino. I'll be quick. Thank you everyone for being here tonight. Obviously most specifically for the students, but really everybody who's here who helped to create these opportunities for our students. This past school year has been challenging probably for everybody, and I know as parents you have to support students in order for them to succeed. Staff members have to support them in order for them to succeed, administrators. Really it's a lot of people working together to ensure that we get a chance to celebrate their work tonight. So I really, more than anything, want to say I'm proud of you and thank you, and really enjoy the night. And to our graduating seniors, thank you so much for adding so much to our school district. Don't be strangers, and best of luck moving forward. Have a great night.
4 years goes by pretty fast, but I have the unique opportunity to remember you guys in 6th grade in Tech Revolution when we were building the Rube Goldberg project, and then in 7th grade when you were in robotics, and 8th grade as you kind of learned a little bit about what computer science was all about. And then you had the opportunities to go on interviews for the STEM Academy, sit with Mr. Murick and learn from Mr. Locatell and Ms. Froelich, and have an experience here at the high school that was really a unique, in more ways than one, unique experience. And now here you are tonight, getting ready to celebrate all that you've done together and individually. And as I watched you guys interact with one another, outside of all of this hard work, you've become a family. And you've become brothers and sisters with each other, friendships that are going to last, hopefully, for the rest of your lives. Right? You'll get together and have STEM Academy reunions and talk about the times that you had when you were in high school. And that's really the purpose of what the Academy is really designed to do. It's designed to create opportunities for you to find out who you are, to build relationships, and to figure out if this is really what you want to do with the rest of your life. And I think for a majority of you, your passions are really about your creativity, your ability to problem solve, and to collaborate. And whether or not you go on to an engineering field or a math field or a science field, those are skills that you're going to take with you wherever you go. I have no idea how you've been able to do all these projects with the challenges that you've been faced with, but you've risen to those challenges every step of the way. And your perseverance, your dedication, your commitment, it's a testament to who you are as students, your families, and the support. Thank you, parents, for being here tonight. Thank you to our staff who have dedicated a tremendous amount of time. To have Mr. J here tonight, even he's been filling in different roles, and just how much he's appreciated watching you grow. So enjoy tonight, have fun with it. As much as this is a capstone of your work, it's a celebration of your work. And so enjoy it, and thank you for all that you've done to make the STEM Academy what it is today, and for the legacy that you're going to leave for those that follow you. Right? Because this Academy is going to continue, and the students that are a part of it are going to be working to live up to your expectations. So thank you for keeping those expectations high. Thank you for being just great young men and women. I know I'm going to miss you terribly when you go, because you've been just wonderful leaders for our building overall. And so thank you for being a part of my life for this period of time we've been together. And I'm looking forward to hearing about your presentations. So congratulations and welcome to everyone. So I think without further ado, Ms. Bernadino, who's going to start us off? Oh, there is one person that I do want to thank. I told him I was going to embarrass him, but I do want to thank Mr. Honig. Mr. Honig took on an incredible challenge of picking up the capstone and being there, for the students as they went through the project and putting this night together. So, Mr. Honig, thank you for your tireless dedication and commitment to make this happen tonight as well. So, Mr. Honig is kind of our MC. He's going to be introducing everything. Thank you for Mr. Muir for being here, Mr. Locatell for coming back, Ms. Froelich for all that you've done for our students. And without further ado, we have Mr. Honig.
As most of you know, I'm very few words. But I do want to just take this opportunity to thank everybody for, of course, being here tonight and supporting these guys. Most of you know I'm an avid fan of Legos. And the Lego model, in case you didn't know, is, I'm going to try to say this in Danish, but it's probably not going to go well. Die beste ikke forgot. And if you didn't know what that means, most people don't, it means that only the best is good enough. So now I'm about to present to you the best of the best. And to start us off, Kyle, all you.
Hello, I'm Kyle, and here's my water damage mitigation project. So here's basically a timeline of the year. In the beginning of the year, we were tasked to come up with some problems that we had to solve. We started out with 12 problems, and we narrowed it down to 4, and then ultimately picked 1 at the end. So once we picked that one problem, we had to collect data and do some research on the problem to learn more about it. After learning more about it and really getting a grasp on the problem, we moved on to sketching and 3D ideation, whether this was by hand or on the computer using different programs. The next step was then prototyping, once we selected one of our designs from the sketches, and then we came to an end result. So what was my goal when solving the problem? So my goal was to minimize water damage in homes in order to save homeowners time and money during floods. So during my research, I came up with some statistics. So 40% of natural disasters happen to be floods. 98% of homes in the US experience some sort of water damage throughout their lifetime. And 9 out of 10 US homes do not have flood insurance, so this plays a big impact on the financial aspect of it. So along collecting data, so I conducted some interviews to people who have experienced flood damage to get a better understanding of what happens when it floods. And during this research, I also found an efficient and the safest way to inflate my barrier system to block the floods from reaching the house. So here are some of my ideation sketches. So this was very early in the process. We had to come up with 4 sketches. As you can see, it was just hand-drawn, just a very rough draft. But it was just coming up with ideas to get our minds flowing and just come up with a basic idea that we wanted to pursue. So we had 4 versions of it. I'm not going to go into detail on them because they're very basic. But as the process continued, we narrowed it down and selected one. So then 3D models, we used the computer to do that, different programs. I used a program called Onshape to do my model. So here's my original model. This is the first one I made. You can see here, I'm focusing on a box system in order to take the floodwater and actually pump it into a barrier system in order to block the water. So you got here a pipe that the water goes into the box, and then on the top of the box you see that little box-like shape. That's the pump. So the pump's going to take the water and pump it through a pipe, through a check valve into the barrier system, and the barrier system will then block the water. So this was just the original model, which I came across some problems during that. So I had to change it, and here's my final model. So as you can see some changes, I added more vents, I guess you could call them, on the side of the boxes to allow the water to get into the box. You can see I moved the pump from the top of the box to the bottom to allow it to activate faster, because in the pump there's a flow switch which turns on the pump. And also you can see the box is sunken into the ground. I wanted to bury it into the ground so the box will fill up faster and it'll activate quicker. So here are the drains that you saw on the sides of the boxes. I designed these on Onshape and 3D printed them. Here's the stand that the pump sits on inside the box to allow the box to fill up a little bit, and then once it reaches that certain height, then the pump turns on. Here are washers that I used for the tubing and the check valve. I made washers and 3D printed them in order to have a tight fit with the tubing and the box. So here's some prototyping that I did. So here's some pictures. On the left here, you have a heat gun, and I was molding the tubing to the pump. Here are the vents that I 3D printed to allow the water to enter the box. And you see the orange tape, that's what's like deciding how far under the ground the box is gonna go. And then you see on the bottom right here, there's the check valve, the gold thing. And then there's a black washer right here. That's the washer to keep it snug against the box. So then I came up with the final product. So here's my final product. I had to test it in a sink because it's hard to come up with like a flood conditions. But here's the barrier system when it's inflated, and that's the water inside, which that would be flood water in a real situation. And here's the testing. So I just filled up the sink with water so it acted like a flood. And as you can see in the video, the pump is pumping the water through the tube into the barrier system, which is filling up the inflatable. It took a few minutes to inflate, but this is the final product. It inflates and it creates a barrier system to block the water. Some future improvements that I would use going like next time or continuing to pursue this problem. So the power system, right now I just use the plug and like an outlet, but obviously in a flood there would not be power to do that. So I'd want to replace it with like some battery so it could work while there's no power at the house. And also I'd want to make it easier to clean up after it's done using. So all the water would be in the tube, and it's hard to get out of the tube. So I'd want an easier way to release the water after it's done. And thank you for listening. Next up, I'd like to welcome Mr. Owen Casey.
Hello, my name is Owen Casey. My capstone project is the all-purpose prosthetic foot. So you're going to hear this a lot tonight, but the project overview is a problem ideation, researching, sketching, rendering, and prototyping. So first we have problem ideation. Defining the process. So I ran into 4 main problems in the prosthetics industry during my research, and that would be durability, accessibility, cost, and versatility. So durability meaning prosthetics only last like 1 to 3 years. So we need to up that, obviously, if they cost $5,000 to $10,000, which I'll get to later. Accessibility, there's 40 million people that do not have access to prosthetics, and 5% of those can afford them. So obviously, if you see people, they'll have prosthetic, but you have to think of the third world countries, developing nations that don't have access to these. Here again, we have costs, $5,000 to $10,000, and that's including base prosthetics and not neurological things that connect to the brain to move. So we have versatility, and this is aimed at amputee athletes. So you might see the running blade and other prosthetic additions that make it easier for them to move. I wanted to make it all-purpose. Everyone can use it, even if you need other specifications. So here we have researching, and then this is from Rebecca Smith, who is a orthopedist from Prosthetics in Motion, which is a prosthetics manufacturing plant based out of New York. So she says there are lots and lots of prosthetic feet available depending on a person's activity level, what specific activities they want to be participating in, if they need a foot to be waterproof. So characteristics that depend on cost, they depend on durability and materials. And these are more quotes from her. She basically just outlines that a big part of the cost is insurance coverage. Not a lot of insurance agencies will cover prosthetics, especially in developing nations. So now we get into the materials of this. So first we have EVA foam, which is cost-effective, high-density foam. When applied heat to it and it cools, it will keep its shape, which is what I'm looking for. And then carbon fiber, which is carbon fiber. You attach to the thing and then you cure it with epoxy resin. So we have here why I chose carbon fiber. Modulus is just a fancy word for how much it'll spring back to normal place. So if you bend it, it'll go back very quickly. So we see carbon fiber on the left that has a lot of strength and modulus. Here we have raw materials, carbon fiber, epoxy resin and hardener, EVA foam, heat gun, and Dremel. Now we have sketching. So the red circles outline my main points of interest. So here would be where I want the energy return to go. So if I wanted it to be in the bottom half or in the top half, where I wanted all the energy to concentrate to, so that would have a ultimate release. And these are more sketches. Now we have rendering. So here is the design. It was designed in Inventor and Onshape. And we have all the different components, carbon fiber arch, bolts, carbon fiber spine, and the socket. So it's a universal socket. I guess everyone agreed to use the same socket so that all prosthetics can be used together. This is my design too. Same thing, but the energy return is more on that half of it rather than the bottom half. So I ultimately decided on design 2 for it. So this print here is to mold the EVA foam. So we heated up the EVA foam, put it to the thing, molded it, let it cool, and then we had a basis for our foot. So design process, this is just what we used. So we have the model versus the print, and then the white outline is just so that it would fit into it, so I had the specific dimensions for it. And then, again, same thing. Applying heat. So this is the fun part. This is applying epoxy resin to carbon fiber, which is very hard, not given the proper things. So I had to paint the resin on in a thin coat and then lay the carbon fiber 12 onto it and then paint it on again and then let it harden in a specific environment. So we have the second layer here and then the third layer. And then finally we add a tape to it that hardens over time if given direct heat. So this just adds onto it, makes it more stable. Although it did add some weight to it, which is not preferred. Heel and sole, these are the materials that we use for the heel and sole. This is the basis of the heel, made out of EVA foam. It is then attached to it. We put grip tape on the bottom of it, so that it would not slide around. It's the finished prototype. Then future improvements. So given the right stuff, it would have been a lot easier, specifically a vacuum seal. So most prosthetics, when they have carbon fiber applied to them, they could put in a vacuum seal so that all the resin seeks in evenly into the carbon fiber. So that would have been a big help. Didn't really have that, but thank you. I would like to introduce Mr. Michael Gale.
Thank you, Owen, and thank you all for coming. And
this is my STEM capstone. It's the autonomous firefighting robot. And this is the timeline I basically had for the year, and my presentation is going to mirror this very much. So first we're going to come up with our initial question, we're going to research a little bit, have a few interviews. We're going to brainstorm with some sketches and renders. We're going to prototype our 3 systems, and I'm going to show off my final product at the end. And it all starts with our initial question, what are unattended house fires? Basically, unattended house fires are fires that start at home when the owner is not present at the fire. So for example, you'll be cooking at home and then you'll leave the house, the oven's still on, starts into a fire. And unattended house fires are the real deal because there are over 400,000 fires across the country in America. And 89% of these are unattended house fires, so they tend to pose a giant risk to homes. And getting more into the weeds of it, about 7.3% of these fires are based off electrical fires, 30% of them originate in the kitchen when you're cooking. 11.5% of them are unintentional, basically the same category as electrical, just different appliances. But I'm going to focus today on the 40.5%, the unanswered house fires. That's when the owner isn't home and no one really knows where the fire originates from. So I needed to do some research for this project. I needed to interview the most tenured, veteran, experienced firefighter we had in this town. So introducing Anthony Knopf. He's got a pretty appalling resume, over 200 calls himself, and he's graduated from the Morris County Fire Academy. And he says that Pequannock alone faces roughly 5 house fires a year. And he told me that the best solution for unattended house fires are sprinkler systems. I don't know about you, but I do not want that in the ceiling of my house. So I needed to come up with a solution that was either one of 2 things: a permanent installation that was aesthetically pleasing, or something that can be stored away and be taken out when you're not home. And I opted for the second option. So here's some of my sketches and renders. It's pretty tough to show off your sketches when you're going after Owen, but just do it for the end. I mean, I hope they're good enough that you can see 3 common themes. We got a hose in the bottom left, that's my aiming system. We got a Roomba-based system on the bottom right, and then a robot-based system in the top left. And then we have like a fire retardant area where it's either a fire extinguisher or a jar of water. And this is my first render. It's very rough, but you can still see these 3 systems in place. You got a camera, you got a navigation system, and you got your retardant holding jug. And so this led to my prototyping stage. This is where we really develop these 3 systems. So our first system is a navigation system. First off, we have the Arduino was the most important part of my project because it allowed each of these 3 systems to operate on its own. And without it, my project would not come to life. First off, we have the navigation system. So this is a Vex Robot chassis. And it was really good for 2 reasons. Number 1, very durable, very strong. It's made out of metal. But number 2, you can see a bunch of holes in the top, the bottom, and all the sides. And that allowed me to screw in any mounts that I wanted virtually anywhere on the robot. And this is paired with a Vex Ender, no, Vex EDR. And this is like the nucleus of my project. It allowed all 3 of my systems to communicate with each other all at once in that one GPU. And so my navigation system needed a way to communicate with the fire and find where it is. So at first I decided to have a security camera connect to RCA cables, connect to RCA to HDMI converter, to an HDMI transmitter, to an HDMI receiver, to an HDMI USB, not to be confused with the RCA USB, a cord, a Vex EDR, and then it would all lead to a fire searching mask, as it's called. You see a percentage here. You can see a percentage here, it says 0.98, and that's because the image that the security camera comes up with, it would upload it to a database full of pictures of fire, and it would compare them to see if the image truly was a fire. But given that this would send me back $500, I don't think Ms. Bernardino would like that very much. I opted for a basic Arduino camera, only $20. And this is not something you want to take pictures of the family with. It's very weak. In fact, it's only 480 times 320. But I coded the image to go into thermal or infrared to a filter. And so instead of coding the robot to find a fire, I was only needed to code the robot to find red pixels as opposed to a whole fire. And this would all lead to my second system, the nozzle aiming system. So it all begins with this one giant black cylinder, 6 inches tall, and it would hold my fire hydrant. But this alone obviously wouldn't find the fire by itself. It would need a nozzle aiming system. So my navigation system, it would take a picture. If there was a fire, then it would go towards it, but if there wasn't a fire, it would move right 30 degrees. And the process would repeat until it found a fire. Because the robot would only move 30 degrees, in between those two rotations, there'd be a 15-degree difference. So this servo motor at the top of my tower, which is multifunctional because the camera goes on the tower, it would allow for my robot to shoot the retardant in the 15-degree intervals to the left and to the right. And this was the second most important part of my robot. This is a Arduino fire detecting infrared system. And what it would do is that it would be mounted on the fire hose, and when it would swing to the left and right as the tower would make it do, it would find the fire and it would focus on it. This was also responsible for when my robot would go towards the fire, this would stop the robot in front of the fire so it doesn't drive into the fire. And it also has a third function I'll get into later. This is the nozzle aiming system altogether. But once again, this was also responsible for setting off my third system, which would activate the fire hydrant. So these were all the pieces that brought the activation system to life. We got string, we have a on-shape design mount, we got a rod and another servo motor. And it ended up looking like this. The servo motor is right here on the bottom. And it would rotate the string, pulling off the pin to the right, and it would squeeze the clamp on top, setting off the fire hydrant. And so this would all lead to my final product. So here it is in person. And it's got a few flaws in it because let's say I have a coffee table at home, it wouldn't be able to see past the coffee table. So it would need to be fixed in the way that maybe we could map it around the coffee table next time. It could map its environment out and then track the fire from there. And it could also use a makeover. There's a lot of wires, so before it goes on the shelves, you could use a makeover. And that's about it. So thank you. Connor Griffith.
Hello, everyone. So my project is the UV office light sanitizer. So similarly to everyone else, I also have a design process. It started with the problem ideation. We came up with 4 different ideas, and it moved into the project planning after that, and into prototyping, and then the final product. So how did my project come to fruition? When I originally thought of my project, it was around when COVID was still booming. It was still an issue. Obviously now it's dying down. It's hope that it's still dying down. But that's how I thought of it. I wanted to give people a safe outlet to not have to worry about COVID and like feel overall safer where they were. So facts from the CDC. So on the CDC website, they describe 2 different surfaces. They're called foamite surfaces, but more specifically, they're porous and non-porous surfaces. Non-porous surfaces are things that like have breathable holes, like cloth in your clothing. The virus and any other like flu virus would only last like maybe minutes on there, like 10, 15 minutes on there. But the other type of surface is porous surfaces, and that's plastic, wood, or metal, and basically any type of office supplies, scissors, pens, pencils, anything like that. And viruses last from days to even weeks on those. So, yeah. So for my project, the things that could currently be done was use soap and detergent, like wash doorknobs frequently, don't use doorknobs frequently, avoid these things, and also create a cleaning routine. So For my expert that I wanted to research, I looked to our fellow communities and to our secretary at SJG Elementary School, and she was Chrissy Beach. I asked her what her process was for cleaning office supplies, and she said Mrs. Arena and I typically just use our own pens in the office. If a kid comes in to use the pens or pencils, we try our best to wipe them down, despite the annoying and tedious process. And then I asked the second question, do you differentiate your office pens into a clean and dirty pile? If not, have you seen this in other offices? And she clearly said that she did not differentiate clean and dirty pens. So my ideation sketches, as you'll see shortly, they are much better than Owen's. I don't even know how to describe this one. I originally thought it was of a hot dog cooker idea. It clearly did not work out. This one was more prevalent to what I chose for my final project. It was a box, had a dispensary tray. You'd put a pen or pencil in there, it would clean it for a certain amount of time, and it would pop out into the tray. And then this also was similar, it just popped out into a cup instead. So my materials that I used was an Arduino Mega. It's basically a regular Arduino board, but has more pinouts because I used a bunch of lights. I used 20 lights exactly to clean whatever you want to put in it. The code that I wrote on it was written with C++. I also used PLA filament to 3D print all, like the box, not the plexiglass on it, but everything else. I used UV lights to kill the bacteria and germs. I used a singular servo motor, and it was able to communicate with the Arduino Mega and rotate 360 degrees. A solid wire was used for all soldering for all my lights, and it was eliminated the need for a breadboard. And I used resistors, and they are able to regulate the flow of my electrical current, and it also was able to keep the flow within a 5-volt threshold because each pinout can only max out at 5 volts without frying the board. Onto my 3D renders. This is the tube that I created. It was very annoying and tedious to create because of all the lights that I had to put in it, but you can see there's 20 lights revolving down the tube. So this is the top door. On these 5 pegs, there's little fins, I guess you could call them. They're all attached to it, and it'll open with a gear, as you'll see. This is the gear. It allows these holes allow for 360 degrees of rotation. And then I also need to create a smaller gear that turn the bigger aperture gear. These are the doors. They have a unique design to fit into each other. And the slot right here is to allow the gear to smoothly rotate these fins. This is simply just the bottom and top of the case, and then the plexiglass on all 4 sides fit here, and it's an 1/8 of an inch offset. So on to coding. This is the first part of my code. It's just simply the integers and outputs of the code. On the bottom, you can see all the pin modes. Those are just coding for all the lights. They are assigned a specific number, and later in the code, if you want to code a light to do a specific thing, you just simply refer to it as the number that it's designated to. Counter and while loops were included into it. And also at the bottom of it, you could see the pattern that was written for the lights. And on the next slide, it shows the lengthiness of it. Basically, when one light turns on, the second light will also turn on. And then while those 2 are on, the third light will turn on. And while the third light turns on, the first light will turn off. And just keeps going down the line until it gets to all 20. And then finally, it's just resetting back to the initial state at the end of the code. So on to prototyping. This is what I was talking about when I mentioned breadboard earlier in the presentation. This was just to test out all the lights and resistors and pinouts before I actually used solid wire to solder everything together. you can see here all the wires that I had to use for all 20 different lights. This is the tube. When I actually got into soldering, I had to create a ground wire that wrapped all the way down around the tube to connect all the lights back into a negative ground channel. All the lights are hot glued inside, and the negative side is connected to the resistor with 330k ohm resistors. Here's the light demonstration. Goes down in the spiral pattern. So putting it all together, in the images on the left, you can see how messy it is. The middle image is before I was soldering it all. I had to use 3 different breadboards. And then on the right, you can see it finally coming together. It is a big mess with zip ties and wires everywhere. And onto my finished prototype. I have plexiglass on all four sides of it, and in the back, right here, you can see a push button that I use to open the door, and then close it. When the door closes, the lights will turn on and go in the spiral 10 times, approximately 30 seconds. So my flaws and future improvements of my design. The wiring, it's clearly a big mess, and when I was trying to fit it into the case, the soldering isn't the best for staying together. A lot of wires would pop off, and I'd get really annoyed, and I have to put it all back together. Mr. Honig said it would be the easiest part. And also the tube. The tube was rather large, and this would prove to be inconvenient on school desks or office spaces. It's rather bulky. A smaller tube would be more convenient for most people. And that's it. Now I would like to welcome Morgan Howard.
It's a little tall. All right. That is not fully loaded. Just gonna give a second. Say hello, everyone. Thank you all for coming. He didn't get a lot of thanks before, so I'd like to thank Mr. Honig for putting up with all of us for the whole year. And I'm gonna start with your C's. Anyways, so as you see here, the title of my project is Sound Filtering Aid. We'll figure out what that is in a minute. Like everyone else's project, I set it up in 4 different sections, the beginning being the start of my project and defining the problem that I wanted to tackle and doing research on it. The next section being planning the project by brainstorming my solution and sketching my ideations. The next step being designing my project physically by creating a prototype and testing its failures. And last but not least, finalizing my project and coming up with any changes by testing the product and adjusting its weaknesses. So the origin of my project stems from my childhood. For those of you who don't know, I have a younger brother who was diagnosed with Trichomonas microtia. It's nothing too crazy, don't think it's anything bad. But as you can see here, there are images of 2 babies here, one with a fully functioning ear. As we see here, it's pretty normal, full outer ear, full ear canal. But up here, it's a complete lack of an outer ear and an ear canal. So I did some research with the California Ear Institute, and I spoke with a woman named Haley. I will not try to pronounce that very Greek last name. But she basically just said that children who suffer with a Trichomonas microtia, their speech comprehension drops from 95% to 60%. So obviously some of the damaging effects of this would be hearing loss, which could lead to a speech impediment, especially since you're born with this. It could stunt the development of your speech as a child and set you back in a classroom setting. And the only current solutions now are 2 types of surgery: a physical surgery that uses a rib graft to externally reconstruct your ear, and the other one being a drill into the side of your face. A lot of parents don't really want to put their kids through that, which I understand. The only other solution to tackle this would be a hearing aid, but again, children can become very overwhelmed
when they haven't been able to hear their whole lives, and then all of a sudden sound just comes rushing to them. So a lot of people opt not to do that. So essentially the goal of my project was surrounded by a classroom setting, and I wanted to filter noise to diminish distractions for a child in a classroom, and by filtering sound to only hear a teacher's voice. So when I started planning my project, I came up with 3 ideations. None of them I actually chose. I just combined the things I liked about each of them into a final render. So as you can see here, those are circled. In this one, that would be the Bluetooth connection. This one would be the sound detection software or the audio filtering software that I decided to use. And this one would just be the accessibility and functionality of using buttons. So this is one of my earliest ideation renders. I wanted to first incorporate a microcomputer into the speaker so the sound would be filtered right by the child's ear. However, that proved to be a little too difficult for me. So I decided to move my project into 2 parts. The first part being a Bluetooth bone conduction headset. As you see here, this is one of my renders of it. Here are some of the buttons that I use for the Bluetooth connection, and the front part is the bone conductions. It's just another angle of it. So then I actually started to physically design my product and prototype. So first I had to lay out a budget that I wanted to use. I only bought 5 things, really only 4. First being an actual fully functioning Bluetooth headset that I then reconstructed. Next being a Raspberry Pi, which is a computer with its own operating system. The next being 2 USB microphones, and I also use tools. As you can see, I skipped the base GPU because that is 3D printing filament that is tan and it's rubbery. And at first I wanted to go with a sort of physical appearance solution, but I decided to not go that route, so I just wasted Honig's $30. So here's a prototype after I took it apart. As you can see here, there originally was a left and a right ear speaker, but I took it apart so that it would only be the right side because a microchip only affects one side of your ear, typically the right side. So as you can see, it looks kind of messy, but it's just a motherboard inside of casing and a bunch of wires to a battery. Here's just a closer look. There's an LED that detects Bluetooth, and then the battery is pretty chunky. So this is the Raspberry Pi. It is similar to, or it looks like an Arduino, but it actually is a fully functioning computer. It's just a small scale computer. It's about that big. The only thing that I changed about it was I added 2 USB microphones. One of them is not pictured because it's on one of the wires. You can see there, it's on a USB extender because the 2 microphones cannot be close enough to each other or else it'll create a lot of interference. This is just the back. As you can see down there is my SD card, and that has its own operating system on it. And this was the early stages of my coding on the Raspberry Pi. I used, at first, up here, that's the Raspberry Pi coding terminal, and I used it to find the IP address of the USB microphones. And then down here, I went onto the MATLAB Simulink program, and I ran that on the Raspberry Pi to actually connect the software with the USB microphones. And then here's actually what the coding terminal looks like. That's how I set up the microphones. Here on the left side, on the top, it's ambient noise microphone, which basically is attached to the extendable USB. And all of that noise is filtered and then diminished to almost 0. And then the voice signaling microphone, which picks up only certain frequencies of sound, basically similar to a speaking voice, and it amplifies it. So then I went to the finalization of my project, and as you can see here, I developed a code in Python for recording the sound, just to test it for myself. And here's my little demonstration, I guess. These are the audio signals side by side. The one on the left, as you can see, it's not very constant. The amplitudes are very high. That's because it's detecting all of the sound in a room. But then on the right, as you can see, it's a lot more constant and not as high. That's because it's only detecting one wave of sound, similar to a speaking voice. So this is what my headset ended up looking like. It's a little messy because I had to hide the wires inside the casing, and the battery was too big to fit inside of that. But here it is in all its glory. And then this is just a Raspberry Pi. It just has a case on it. Again, I got rid of the Ethernet cable because I connected it to our lovely school Wi-Fi that doesn't work that well. Sorry, Ms. Rosa. And as you can see, the other USB is not pictured because it's attached to one of the USB extenders down there. So any changes that I would make to this, there's not a lot. I just, again, would use a smaller battery because the other battery did not fit and make it look a little more physically appealing. And also, I would probably learn a little more about coding. Thank you, Ms. Froelich, for teaching me how to code in like a week. But I would like a little more background knowledge before I started another project like this. So, thank you. Now I'm going to call up Lucas Nasian.
Evening, everyone. I'm going to hold the microphone. So. Seamless. Okay, well, thank you everyone for coming to see what we've been working on for the year. So I'm going to get on with my project. So when we were going through ideas for the beginning of the year, I really felt really passionate about one of them. Because honestly, the world needs Iron Man. It's obvious. I mean, it really, there's no question about it. I mean, the solutions are countless, but most of all, it's a real superhero. And I think we can all agree that the world needs a superhero. But as I started to mull this over a bit, I realized that, oh, the exoskeleton is made of a gold to titanium alloy, both very expensive precious metals. And there's actuated weapons of mass destruction on the arm. And those are muon or pulsars, and if you haven't heard of muons before, that's a good indication that this probably isn't possible for me to do. And just to really seal the deal, on the chest is a fusion reactor. Now, fusion technology has not been invented, so I had to humble myself and say, I'm probably not going to invent fusion technology. So I decided to take a step down to handling wildfires, which I think is just a little bit lower, I think. So first, I'm going to define the problem for you, just to really show how severe wildfires can get. And next, I'm going to go over my process working towards a solution, and finally, what I've arrived at this time. So, fortunately for myself, I was able to get in contact with someone from the Department of the Interior, if you can believe that. So I found out these rather jarring statistics. 4.5 million acres are burned every year, mostly in California, which you probably heard on the news a few times. As of 2019, there are over 50,000 single instances of wildfires, also mostly in California. Over $1.5 billion of federal spending is used to fight these fires. That does not count state expenditure. So obviously the money is a lot. Oops, sorry. Causes of these fires include lightning, extreme drought, which is probably the biggest cause, man-made fires in the cases of certain gender reveal parties, and in rare cases, volcanic events too. The biggest problem with these fires is the extreme CO2 emissions, which causes extreme drought, and you can see how this can get worse and worse, and it is getting worse and worse. So also from the lady from the Interior, she also told me about what is being done about these fires currently. So, as shown in the wonderful film Planes, Fire and Rescue, we know that aerial extinguishment is a method in which planes fly over these forests in flames, and they dump classically red fire retardant all over. And in other places, specifically outside the fire, there is targeted deforestation in which a belt is carved around the area so that the fire cannot spread to more of the wooded area. So improvements we can make to this existing solution is, number one, it's reactive, right? The fire has to start and get large enough to be noticed before anything is done, and that is a fatal flaw, and that's why there's so much damage attributed to these fires. To get the men and women in harm's way out of the harm's way, I decided to try to have something that's remote, something that is present at a potential fire that could get rid of it quickly. something that is electricity free, and something that is tileable. Now what does tileable mean? It simply means something that can be duplicated and spread across a large area. So I decided to come up with two design constraints to focus on these improvements, one of them being electricity free to make it super cheap, and the other being proactive. So I started with this first design, which was a centrifuge mounted on a very large post. Essentially, it was a disc that would spin and spew fire retardant when there was a fire detected nearby. The main problem with this is that the effective range decreased quadratically with height. Now, if that sounds like gibberish, don't worry, I'll explain. Two graphs. Things fall in parabolic arcs, which are these U things. 10 meters effective radius, 20 meters effective radius. You can see the jarring difference in height here. So the you have to double your effective radius, or how much area is covered by the retardant, you would have to quadruple the height of the tower, which eventually that gets unsustainable. So the second design, I decided to go closer to the ground, in which a plane would fly overhead and drop essentially these lawn darts on the ground, and they would be in close proximity to the ground, and the foliage on the ground is what brings the fire. It's not really the trees burning, it's the bushes on the ground that really bring the fire. So this would take care of that. Now, the game lawn darts was banned in the US for a reason, because giant metal spikes falling from the sky is not really ideal for a national park. So I decided to come up with something a bit more safer and less ballistic. A fire retardant claymore. Now, please don't be scared of the word claymore. I'll explain what that means. So it's a large radius but a low height off the ground, so it solves the problem with the first. It is a sustainable and rechargeable chemical reaction that drives it. It can be deployed by land, by people, or by air. It is a high concentration dispersal, so there's a lot of retardant in a small area to ensure extinguishing. Low risk and no electricity. There are a few weaknesses down there that I'll get to when I talk about the design. So we moved on to sketching. On the left is some chemistry, which I'll get to later. And on the right is the essential concept of it. So here is beautifully illustrated fire on the ground. And then here is smoke indicating that the fire is no longer there. Essentially, you can see here that we have a shaft with a bulb on top, and then the bulb would explode and retardant would be sent in all directions. Now, getting to what is in the middle, we have modeling, 3D modeling in Autodesk Inventor, and rendering, and you can see this starting really to come together here. So, explaining how this works. So basically, it is a large copper pipe that is placed into the ground, highly thermally conductive. When a fire rolls by, it will heat the copper pipe and transfer the heat inside the bulb at the top. Inside is a wax capsule filled with acetic acid. Please don't be alarmed by the word acid. It is this compound right here. That acid will leak out of the melting wax capsule into the surrounding sodium bicarbonate. The ensuing chemical reaction, this is the sodium bicarbonate, the ensuing chemical reaction will create lots of internal pressure, which will then fragment the bulb, and the unreacted sodium bicarbonate, luckily, will also act as a fire retardant. So, there you go. Finally, the application. So you can see this is a high-risk area that I searched up on Google Earth. You can see there's some dry patches on this mount specifically, and those waypoints there are potential placements for this device. And you can see what I meant by tile before. We have a sort of square array of these devices spread out to cover a large area. And you can see the construction process here. So I began by 3D printing a 2D lattice of sorts, and I folded it into a polyhedron, specifically an icosahedron, to emulate a sphere. This here is the wax capsule that will be inside the bulb, and the bulb is capped off and filled with sodium bicarbonate. So you can see these solutions are isolated from each other until the heat melts the capsule and causes them to mix. So thank you very much. If you have any questions about the design itself, I'll be at my table. And I'd just like to thank Mr. Honig for really motivating me through this. So with that, I would like to welcome Olivia Mazes to the front.
Okay, hi, I'm Olivia Mazes, and this is my final capstone presentation, which is called the Lockdown Lightbox. And with everything going on in the world right now, I thought it was really important to focus on school safety. And I divided my project into 3 steps: researching my problem, ideation sketches, and then my final prototype. So first, to research, I just wanted to see how common lockdowns were throughout the country. And because I know our school obviously does them and our state requires them, but I just wanted to know. And I found that 40 plus states require school-based emergency drills. And from the same article, I found a study that analyzed conversations for 114 K through 12 schools, and it said that 42% of teens felt increase in anxiety after active shooter drills because they weren't sure if they were real or not. And then I moved on to my ideation sketches. And my first solution was a system that would connect to the wall near the loudspeaker, and it would use a sound sensor to detect different pitches of sound, and it would light up one light for a drill, and then a different pitch would light up a different light for a real emergency. And here are what my 3D renders look like. And then my next solution would be similar, but instead of using a sound sensor, it would connect to a computer and it would send out via code. And here are my renders for this. And so then for my final product, I went with pretty much the first solution, but I tweaked it a little bit. And here is what my 3D print looks like, the render I used Onshape for this. And then this is my print, and I had a slight problem with this. I didn't print the top to be large enough to fit over the bottom, so I had to sand down the bottom, which took me a really long time. And then this is what the inside of the box looks like. So I have the sound sensor, and it has a potentiometer on it, which is the blue part right there. So it can adjust the amount of sound coming in, so you can eliminate the background noise, or most of it. And then it has a breadboard with an RGB LED resistors, wires that connect to the Arduino ports, and then, as I said, it has a sound sensor. And so then to test, I use this tune generator, and it basically uses different frequencies to detect the LEDs. And so the blue LED would represent the drill in this case, and the closest frequency to that to detect the LED would be 700 hertz. And then for the green, which was the real emergency, it would be 1000 hertz. And then to turn the lights off, it would be 1300 hertz. And so some problems I ran into along the way, besides the sanding issue, was I first started off with this sound sensor right here. And as you can see, it doesn't have the potentiometer that the other one has. And so it wouldn't eliminate the background noise, and so it would keep the light on all the time. And so this was my first idea. And so as you can see, the blue light would stay on because too much sound was coming in. And then it would turn on the other light, but then that would turn off right away. And then similar to this was this idea. It had 2 separate LEDs, and the only thing it would light up was the blue light, so I had to change that as well. So now I have my demonstration. And for this, I'm going to show the different tunes and the frequencies of them to light up the different lights. And for testing purposes, I didn't have the box fully sealed. I have everything inside of it, so I'm going to take that out to show the testing. And this is also, it's battery powered. Sorry, this is taking a little while to load.
So I'm going to start off testing the green light, which would be the real emergency, and then I'm going to switch to the blue, and then I'm going to turn it off. So I have to get it close enough to the speaker so that it lights up. Sorry for the loud noise. So then some future improvements. So just for testing purposes, as I said before, I didn't have it actually inside the box, like fully used, but I would solder the LED off of the breadboard, and then I would drill a hole in the top of the box so that the light could shine through that. And then I would organize it better so that the sound sensor could be close enough to the loudspeaker so that it could pick up the sound clearly. And that's it. Now I want to welcome Kate Sack-Dallin.
I'll give Olivia a minute. Sorry, no rush. All right, hi everyone. Thank you for coming tonight. And my name is Kate Sack-Dallin. I will be presenting my final capstone presentation, which tackles the problem of accessibility in schools for students with cerebral palsy. So just to outline the process again of this entire school year, we first began in September with research, and then we moved on in January to making our ideations and sketches. And by February, we began the prototyping process, which meant building with a lot of problems and failed models. So now I'm going to get into some of my own research. And in order to tackle a problem so large as cerebral palsy, I wanted to make sure I got a good understanding of what it actually is. And so as you can see here in my diagram, the severity of the cases get worse going left to right. So different parts of your body can be affected, which means you are paralyzed in the white areas in the model. Along with the different types of cerebral palsy that affect where your body is, it also acts with motor types, which affect different parts of your brain. And as you can see, there are multiple different areas that are affected, and this can cause a variety of different issues, whether it's balance and coordination or high muscle tone and jerky movements. It's really a wide scope of a problem to tackle. So now I'm going to get into some of my ideation sketches. So my whole project, I planned for it to be wheelchair adaptable, and so as you can see in some of my sketches, they do have wheelchairs and how it would fit on there. So in my first design, I wanted to make a page turner, and the page would be turned by a wheel mechanism, as you can see in the middle. My second ideation would include inclined planes that had clippers on the side of the book, so the clippers would slowly release pages of the book, causing the page to fall over. And my third and final ideation was an Arduino-powered vacuum pump, which would use suction to lift the pages and turn them using a robotic arm. So I ended up going with the third one, which sounds a lot more complex, and I couldn't tell you why I chose that. Mr. Honig told me I needed a challenge, so here it is. So in order to begin my project, I knew I needed a mechanical arm that would, in fact, work. And so I found the EasyBot arm. The EasyBot arm was made by Carlo Franciscone, who is an Italian design engineer. And he basically released his design of the robot onto a public domain for people like me to make at home. So as you can see, I kind of laid out the different components of the arm itself. So I 3D printed all of the pieces needed for the robot using the 3D printers in our classroom. And it took a lot of failed prints, but ultimately I was able to print all of the pieces successfully. And these are a couple pictures of the arm fully assembled with the MG90 servos at the base here. And I wanted to talk about a couple of components of my project that really are the focal part of it. And one of them is the giant green button, which initiates the entire process of turning the page. And one of the reasons I chose a button so large was mostly to help with kids that have problems with fine motor skills. And I wanted to make sure it was something that they could easily see and easily access on their own to make this more of an individualistic tool that they could use. Next is my circuit, I guess we could call it, of my vacuum pump. So this white cylinder shape is my vacuum pump that supplies the air, and it pushes air into the black tube to the solenoid valve. And the solenoid valve is basically a switch that redirects the flow of the air. So instead of it just flowing straight through, it creates a suction motion going the other way. And through the clear tube, it goes to the vacuum cup level compensator, and that metal piece is what directly is in contact with the book. So my pictures did not load. Okay, so basically what I had over here was a picture of the Arduino Uno board. And it's kind of what Connor touched on a little bit earlier, but it's basically the central hub for where I'm plugging in all the different components of my project. So I'm using 4 boards in total. So the second board is a mini Maestro board, which is where I have connected all of the motors of the robot. And one of my biggest challenges was making sure that the 2 boards would communicate with each other. And that was a real problem that I faced. The picture's loaded, lovely. My third board was a power supply module, and as I'll get into a little later, I had a lot of problems with power. So basically what this does is that it takes external power sources, like an adapter, and it helps you add extra voltage to the project so that it increases the speed of the suction. And over here is my relay module, and as you can see, this is also basically like a switch. These 3 blue spaces on the relay is basically where I plug in all the other boards, and it is a switch that redirects the different places where the current is being used in my project. So I wanted to give a quick layout of what I thought would be a very simple and easy circuit. I thought I could get this done, no problem. It's a couple wires, it's not that bad. So this is what it ended up looking like. As you can tell, it's not a few wires, it's actually one too many. And with the help of Ethan Bernstein and Mr. Honig, they were able to help me understand the board and not only to get it to work as well. And with that, I'm going to go into some of the problems I faced with this project, because it did not go as I planned. First being my power supply. Mr. Honig can attest to this. I not only burned out 1 motor, I burned out 6, which caused a very big problem for my project. And the source of this problem came that I didn't really understand how much power was needed for my project. So I started by connecting 2 pins on the back of the mini Maestro board, thinking it would supply enough voltage, but to my surprise, it did not. It was actually too little, it didn't even move. Then I went to a 12-volt adapter, which, as you can guess, burned out all 6 of my motors. So then I came to a nice little medium of going to a 9-volt adapter, which allows the robot to move slowly and smoothly. Another problem I faced was the vacuum cup level compensator being a little too heavy for my robot arm to handle. And so that's a big part, especially when it comes to coming down to the page. It wasn't able to get back up. So in order to fix this problem, I knew I had to somehow counterweight the weight in the front of my robot to the back. So I included rubber bands, as you can see on the back. And basically this creates a tension in the back of the robot that assists it with coming back up. And now I'm going to show a video of my demonstration. If it will load, I'm very sorry. Thank you. And with that, I do have a lot of future improvements I would like to make if given more time and more resources to continue this project. The first one being organization. As we can tell from the picture of my circuit, it's a little messy. I would like to clean up a lot of the things I did with the wires, and maybe keep them in boxes. And along with that problem comes soldering, and I really wanted to solder wires, that way there would be less and it would look a lot cleaner. Third being my power supply, and no, not because I'm going to burn out motors, it's actually because if this were to go on a wheelchair, realistically it couldn't be plugged into the wall. So I would want this to be battery operated, that way it is mobile and can move wherever the student would like to move. And fourth would be a flipper. I don't know if you can tell in that last video, the page didn't completely turn over, and that's mostly because it needs some sort of assistance to flatten out the page. And if I had more time, I would add that. Thank you so much. And now, let's please give a warm welcome to Sarah Mabey.
Hi, my name is Sarah Mabey, and I made a self-moving toothbrush. So I know we heard it 8 times, but I had the problem ideation, the research, 3D modeling, prototyping, and then result. So my problem was those with restricted motor ability were experiencing dental health issues, and these include tooth decay, plaque, and missing teeth. So I specifically focused on Huntington's, and some of the causes were their access to healthcare, which included transportation, access to facilities, and financial burdens. Another one is a diet. So their diets are very high energy, and they have food supplements that are very high in sugar, which can rot away your teeth. And also the medication they have to take causes dry mouth and can also make it difficult to swallow. So I was going to find a way for those with poor muscular dexterity to practice good dental health. And then for the problem ideation, I'll just go through it fast. So I brainstormed my problems, narrowed down the ideas, researched my problems, did some ideation sketches, and chose an idea. So it's really rough. It's really rough. I just included one because it was a whole thing. But this is kind of what the end of mine was like. So it's basically an adjustable rod. So whoever's using it, they can adjust it. And then a suction cup that would attach to something. So it just sticks to the wall, and you could put your mouth on that mouthpiece right there. And for the 3D modeling, I used a software which was Autodesk Inventor. So these were just a few of my renders. I have the actual mouthpiece, I have the suction cup there, and then I have the vibration motor that I also used. So my original idea was to put these vibration motors in each of the bristles, but I didn't really have the time or funds for that. So my project's definitely a lot more scaled up. And then this is prototyping, so that's setting up the Arduino and coding the Arduino. So the materials I used were an Arduino, the mouthpiece, a vibration motor, wires, and then an ultrasonic sensor, which I'm gonna get into here and explain a little. So it has a transmitter and a receiver, and the transmitter is trig on the actual piece and echo on the other piece. So basically, the trigger pin sends out a high frequency sound wave, and then the echo is when it returns, and that's how you get that T in the equation there. So that's the time it goes there and back, and then the half is just because it's going back and forth. And then you have the constant of speed in the atmosphere, and then that's that equation right there. So here's my code and my circuit. The code, if you see down there, it's the vibration motor is on high when the distance is less than 30 centimeters, and then you can also see the distance equals duration, and then that's the equation that I explained before, and then I just defined all my pins and all that. And then this circuit looks very simple, but I have a lot of wiring, as you can see, not as simple as it looks until around the end. But I started off with a light just to test out if I could code it correctly and if my code was working, so that's where you see the light turning on there. And then I moved on to using 2 breadboards, and then you have the vibration motor, so I was just testing out all that. And then we start to scale it down a little more. So it was like that for a while. So I had the breadboard, the Arduino plugged into the computer, and then the vibration sensor there. And then I had to transfer it to a PCB board to get like a maximum yield on it. And Mr. Honig suggested that I like manufacture one of them, but I didn't think I was able to do that. So we just went with these green PCB boards. And these were errors that I had because with soldering, the solders almost act as wires, and if you get the solder into other holes, it ruins the entire circuit. So that happened to me like 3 times. I blew through 3 of these things. And then this is my final product here. So you have the vibration motor on the mouthpiece, you have the ultrasonic sensor there, and then it's plugged into the Arduino. And future improvements I would make, I didn't make a slide, but definitely scale it down a little, maybe clean up the wires, put it into something, and yeah, that's it. I would now like to introduce Luke Shore.
Hello everyone, my name is Luke Shore, and this is my capstone project, which is the inflatable lifeguard buoy, or what I like to call the FlateBait. I'm very proud of that name, by the way. So here's the project overview. Here's the project overview, which was mainly finding a problem first, collecting data on that problem, creating sketches of possible solutions for the problem, and then developing a prototype of one of those solutions. So here's finding a problem. So the problem I came up with was concerning the lifeguard buoy. So if anyone doesn't know, the lifeguard buoy is a floating device used to give to a victim who is drowning in the water. And it's basically something for them to hold on to as you're dragging them back to shore. And so personally, I am a certified lifeguard at PV Park, the one in town. And this is where I actually noticed the largest problem with the lifeguard buoy, which was that it was very large and tedious, and it got in the way of the save. And when you're going out for a save, you want the save to be as simple and as effective as possible, and you want to get to the victim as fast as possible. And so here's where I came up with my solution, which is the FlateMate. And basically, it's an inflatable lifeguard buoy, and the purpose of it being inflatable is that when it's deflated, it can be packaged in a very small area. And of course, you have the fanny pack, which I use for my project. And that's where I'm packing the inflatable lifeguard buoy until it is actually ready to be inflated once you reach the victim. And of course, the inflation is activated by a CO2 cartridge. And so here's the collecting data. So I interviewed an expert, which was actually my boss. He is the PV Park manager. His name's Tim Hausch. And he was the actual former head lifeguard at the park before he became the manager. And he was also a former beach lifeguard down the shore at the New Jersey shore. So here's what he said. He said, I was a lifeguard down the shore, and we have similar equipment to the ones you use. The buoys there are a bit different, but they are still very large and they get in the way of the save, especially with waves coming at you. So he put a very good point with waves coming at you. You're not only using buoys with like pools and lakes, you're using them in the ocean as well. So you need to have something that can kind of make up for that as well. And so here's some of the materials that I used. I have an inflatable tube, obviously something you need to give something to the victim to hold on to. You have the inflator, which is inflating the tube, and this is where I'm incorporating the CO2 cartridge. You have the fanny pack, which is what you're storing the inflatable tube and the inflator in, and then a rope to kind of connect the fanny pack and the inflatable tube together so that the tube doesn't just like float away. You need to have it connected to you and the victim. And so here are a couple different versions out there of inflators. And so one is push-activated inflators. Simple enough, you push the inflator, it inflates the tube. You have spring-activated inflators, which is where you use the tension of springs to shoot kind of like a puncture into the CO2 cartridge, which inflates the tube. Then you have water-activated. This is kind of new technology. It's very expensive. I kind of didn't go down this route, but basically, once the inflator comes in contact with water, that is when it inflates. And then you have tag inflated. Basically, you're pulling a tag out, and that's what's inflating the tube. And so here is where I get into the rough sketching of my project. I'm not going to go into full detail, but I will explain what different types of inflators I considered. So version 1, you obviously have like a tag right there, which you pull, and it opens the fanny pack. Version 2, I incorporated the press-on inflator. Version 3 is the same as version 1, where you're using a tag pulled, but the only difference here is that it's actually on the tube, the inflator. And then version 4, I kind of demonstrated what a water-activated one would look like. But I didn't go down this route, obviously, because it's too expensive and new technology. So here's where I got into my prototype development. So these were a couple of my early models. As you can see, they're kind of a bit confusing. I'm not going to really explain like how everything works with them. But the one on the left was used with manual, kind of like using your force to actually puncture the CO2 cartridge. But you can't really see it, but that one is the size of a human hand. It's very large for an inflator. You want it to be small so it can fit in the fanny pack. And then the second one on the right kind of simplified it down to being smaller, but there were a lot of moving pieces in the part, and there were problems with air containment as you want the inflator to be air sealed. And so here are 3D printing of like those early models. The left one, as you can see, I kind of gave up because I had a lot of doubts with it. And the right two are the ones for the second model. And I want you to focus on the right picture. That is where I kind of decided to move on, because the more moving pieces there are, the more there is for faulty behavior in the inflator. And so 50% of the time when I was testing it, this piece right here would get caught and it wouldn't hit the third piece, which was supposed to be puncturing the CO2 cartridge. And so here's my third model. This is where I was really confident in using kind of like a hybrid between springs and a tag-pulled inflator. So basically, I would have a pin, and the pin would go through this hole right here into the block, which would suspend the springs. And once that was pulled out, the springs would then launch the block into the CO2 cartridge, which would be screwed in right here, and the air movement would go to the right and out to where the inflator would be. So here's 3D printing. This was like my first prototype that was actually finished. And so I decided to test it and see if I could actually manually puncture the CO2 cartridge. So the setup was basically just clamping down the inflator that I had and putting Post-it notes around it to see where air might leak out, because I do want it to be sealed. So execution, simple enough: suspend the puncture pin in, clear the room, and pull the tag and see if it did puncture. I can also
Count down. All right. Oh God. Keep going. 3, 2, 1. And now
And as you can tell by Mr. Honig's voice, that was a complete and utter failure. So the result of test number 1 obviously was a failed attempt. There was a dent made in the CO2 cartridge. I don't know if you can see it. It's very small in the picture I provided there. But also the plastic point that I 3D printed was dented. So that's not good because you want this to be something you use over and over again. And you don't want that to be damaged at all. So the conclusion I made after this was that I needed a harder substance instead of a 3D printed plastic point. And also I might need a larger distance to gain more momentum for the springs to actually launch into the CO2. So this is where I came up with my refined third model. Basically, I replaced the plastic point with a hard metal point, and I created a kind of like a longer distance. So here's test number 2, same setup and the same exact execution.
All right, so, ready? So, hold it like this. You don't unless, did you actually type that down? Again, that's not full. Yeah. It was only difference. Are we ready to? Ready? 3, 2, 1. L.
So the person who said L was Mr. Owen Casey. So the same thing as the one before, this was another failure. This actually did make a deeper dent into the CO2 cartridge, so it kind of made more hope. But at this point, I was like, okay, I need to consider something else because manually puncturing it wasn't working. So here comes the simplification of my project, which was me considering an existing strategy, which was basically a standard bike inflator. And so the one that's pictured up above is actually the one I'm using now. So here is where I come across my new model. The pink thing that you see there, that's the inflator. It is pretty small, but it will do the job. And so you can obviously see the CO2 cartridge attached to the bike inflator, and what attached the bike inflator to the valve that goes into the actual inflatable tube was an acrylic piece of tube that was air sealed. And here's a further look at what it would look like on a lifeguard buoy. That is me, by the way. And then, so I had to see if the bike inflator would actually inflate the tube, and I wanted to see how fast it would. So this is, of course, I'm screwing in the CO2 cartridge and then pressing down on the inflator. Do not mind the sound, please. So the good thing about this is that it was a successful attempt. A large hole was actually made in the CO2 cartridge right there, very different from what I was trying to manually do before. And that was less than 10 seconds. I didn't really time it because it was just like an inflation test, it wasn't the final test. And the conclusion I made is that this route of my project worked, and I also needed to have protection from the CO2 cartridge because the cartridge actually got very cold. It would give you frostbite if you did touch it because the gas is moving from a small area to a larger area condensation from the CO2 cartridge. And so here's my final test. I like to think that you're a drowning victim and you just hear that. You know you're safe. You know you're safe. But I timed that video. That was my final test. And you can see that was approximately 8 seconds. So it was pretty efficient, pretty fast before you get to the victim. And so here are some future improvements for the project. So obviously the pink inflatable that I have now, it's pretty small. It's probably about like yay big. And you want to have a larger inflatable for larger victims because the one I have now is mainly for children or like smaller people. You want to have it so that it's universal for anybody. And of course, if you want a larger inflatable, you're going to have a faster inflation device because the one I have now, at the rate it's going now, it would probably be like 15 seconds for inflating that one. You want to maintain the fast inflation. And also with a faster inflation device, you would need a larger CO2 cartridge, more air in it, so that you could account for the bigger inflatable. And that is it. Last but not least, Ethan Bernstein.
Hello. Cool. I'm Ethan Bernstein. This is the final presentation. You all have made it. Congratulations. And I am going to be presenting my hand sanitizer dispenser sensor. It rhymes. You've seen this 10 times before, guys. My process was very original. I chose a problem, I drafted the ideations, I prototyped, and then I created a final product. Choosing a problem. There were some considerations that were important to me when choosing a problem. I wasn't going to just choose any old thing. So for the criteria that I considered were the impact that it would have locally and widespread, the possibility of solving, so is this something I can actually do? Because like Lucas mentioned, Iron Man isn't really going to happen. So I'm going to choose something that I can actually do in the scope of this class. Relation to personal interest, I'm going into biomedical engineering, so I was thinking something along the biology route would be pretty cool. And then skills that I would learn throughout the project. There were some things that I did not know before that I now know, which are going to be helpful for me later in my engineering career. So that was important when considering a problem. So I chose MRSA, which is an acronym that stands for methicillin-resistant Staphylococcus aureus, which is a type of bacteria better known as staph bacteria, which can cause staph infections, which are pretty bad. They occur in hospitals a lot of the time, and they're from patient to healthcare worker, or healthcare worker to patient contact, and they can enter the body in the bloodstream through open wounds, or if you have like a dirty bed or something, or if hands aren't washed, the bacteria can just get into your body, and that's not very good. So some fun facts about that is that there were a lot of them, a lot of people who had it died, and then it cost a lot of money. So this was something that I think we should focus on stopping, or at least trying to prevent. I talked to Sandra Petruska, who is a registered nurse at Chilton, right over there. And this was important to me, especially at Chilton, because I looked up one of the databases online, and the staph infection contraction rate at Chilton was actually statistically higher than the average in the United States. So if you don't want to get a staph infection, I would not suggest going to Chilton. And I asked her about why this was such a bad thing. Ooh. I asked her why this was such a bad thing, and it can cause sepsis or septic shock, which can be deadly, which is not something you're looking to experience. So now that I have my problem, I had to think about how I was actually going to go about solving it. So this was my first sketch, and this was an idea that was using a laser that would go across the entrance of a room, and it would sense when someone enters and when someone leaves, so you can tell when they were actually washing their hands. This was for, by the way, all of these ideations are meant to remind and make sure that healthcare workers were actually washing their hands before and after procedures when they were supposed to, because the CDC actually estimates that a minimum of 40% of the time doctors actually wash their hands when they're supposed to, which is a terrifying statistic. This was my second ideation, which I kind of actually went with, and you can see there's a sensor, a card reader on the front, which actually reads when a card is being scanned, so you can tell who actually used the card, and then it would send that information to a database and record when it was actually being used and by whom, and the ID number, the first name, last name, and this is actually the design I ended up going with. So there's no real point of going over the third one. And this is also some of my ideation process. I made these in AutoCAD, and these are 2D models of things that I was going to be laser cutting. And this was a box that all of my electronic components were going to be kept inside of and held inside of. And it was very difficult to actually imagine what it was going to look like in real life. So I had a few different, you can see the corners in the little bubbles. The corners are a little bit different based on what was actually going to work and what was actually not going to work. You'll see, it didn't work a lot. Prototyping. I didn't know a lot about electronics and circuits before this, and again, this was one of the criteria when I chose this. I wanted to learn a lot about electronics, so I spent the first 2 months of this project messing around with Arduinos, and so this first part of the project consisted of figuring out how to use the RFID module, which is basically a card reader. And I got that working. That was pretty cool. That's connecting to the motor of the hand sanitizing dispenser. So when it was used, the Arduino would read the voltage and it would actually sense that it was being used and someone wasn't just scanning their card and walking away. I had to make a volt splitter. I burned through 3 Arduinos before I realized that I was burning through Arduinos, and I decided that was a good point to figure out why they weren't working anymore, and I figured it was probably my fault, and it was. The motor from the hand sanitizer was putting out 12 volts, the Arduino can only handle 5, so I was absolutely frying it. I would actually plug the board in, and the chip would go to over 100 degrees Fahrenheit, and that was pretty hot, and that was not supposed to happen. Oops. And this is what it all looked like thrown together on a breadboard. It was lovely. This is my at-home setup that my parents were thrilled about, having in the house a soldering iron. That was a lot of fun. I did it on cardboard. That probably wasn't smart. This is the box wasteland, like the cardboard wasteland that I had in the classroom after I printed at least 15 different versions of the boxes because they just wouldn't fit together. So I brute forced it, and it does fit together now, so that's lovely. And my final product. That's what it is. It's basically a pre-built hand sanitizer dispenser, which on the side has all my electronic components. It has a card reader. I didn't mention this before. The Arduino itself is a Wi-Fi Arduino, so it all connects through the Wi-Fi, and it sends the information on the card to a database, which is Google Sheets for me. And the way that it actually functions is, these are the electronic components. You scan it, and then it stores that information in the Arduino. There's an if statement. This is set up. There's an if statement right here, where it senses if the hand sanitizer's been used, if the voltage goes through the Arduino, it will take the information stored on the card, and it will push it to an application called Pushing Box, which takes all the variable names. What's stored on the card is first name, last name, ID number. It takes all of that, formats it, and puts it to Google Script, because the Arduino cannot communicate with Google applications directly, so I need Pushing Box. It communicates with the Google Script, which then opens up a link, and then the opening of the link puts everything into a Google Sheet, hopefully very nicely. And so some problems I came across afterwards were that my wire management was very poor. Mr. Honig was angry at me for that, but I kind of just I shoved it in. It's fine. And then you can see on the left here, this arrow, that is a USB, which is necessary to access if you want to change the code on the Arduino. I didn't think about that, so you can't really change the code now. So if you wanted to, in an actual sense, change cards or add more people, you couldn't do that. So my next kind of design would have that if I were to continue this project. I'm extremely hesitant to test it. You can, because it's all Wi-Fi dependent. You can, yeah. Mr. Honig will kindly demonstrate, hopefully, it working. So theoretically, the way that it works, you can see, well, it says that it's working, so that's nice. It's all Wi-Fi dependent, and the Wi-Fi works like 10% of the time in the school. So what you do is you press the card up next to it and then use the hand sanitizer dispenser within, theoretically, like 10 seconds. And then it should, pop up your name on there. It's probably not going to, because the Wi-Fi, again, is very bad in here. I swear it works. Everyone has seen it work, right, guys? So it works, I promise you. It's just extremely annoying with the Wi-Fi, especially in this room. But it takes all the information. You can see it takes the time that it was used, your first name, your last name, and your ID number, and it puts it into this spreadsheet, and you can store it and you can compare it to when doctors are actually supposed to be washing their hands before and after procedures. So, it works in theory and in real life, just not in Pequannock Township High School. No shots fired or anything, it's okay. And yeah, there's a thank you slide at the end, but that's basically it. Sorry, it's okay.
So this is where I might get teary. You guys are amazing. I hope you're so, so proud of yourself. I just stood back there the whole time just in amazement at what you have accomplished. So you should be very proud, and I know you will all be extremely successful in whatever you choose to do in the future. So wishing you all the best of luck. To my STEM graduates for class of 2022. That's where we are. So I'm going to ask the students if they would please quietly go to their tables and get themselves prepared. And all of our guests, thank you so much for being here, for supporting the STEM Academy here at Pequannock Township High School, and for supporting all of the students with what they're doing in school, and I know helping them at home. I think there's probably quite a few parents who are happy to have their dining room tables back. I know specifically Mrs. Griffith is extremely excited to have her dining room table back. So feel free to grab a cookie, some water, a mint from the back, have a walk around, talk to students, ask them questions. They could probably demonstrate for you.
We have a surprise thing. Surprise.
Mr. Honig.
I'm not going to lie to you. I'm going to bring this home to my wife, and I'm going to pretend that I bought them on the way. Yes, guys. Again, all the credit goes to them. I just got to be the lucky person to stand back and yell at them at times. But thank you guys. I very much appreciate it.
I'm going to disagree.
Okay.
And I know Mr. Hazelov said it before, but Mr. Honig really, he stepped up for me and for them and really brought this all together. And you did an amazing job as well, so thank you very much. We appreciate you.